Welcome to the Explainer. If you've ever been tasked with managing a massive, complex project, you know the absolute terror of a highly uncertain timeline. I mean, how do you even plan a project when you genuinely have no idea exactly how long the individual tasks are actually going to take? Well, today we're going to solve that exact problem. We are demystifying PERT, giving you the real mathematical tools to master project uncertainty and literally predict the unpredictable.
Okay, let's dive into this. Here is our roadmap for today. First, an introduction to PERT. Second, the 3 time estimates. Third, the core formulas and calculations. Fourth, analyzing the critical path. Fifth, measuring project schedule risk. And finally, number 6, a comprehensive master example to tie it all together.
So, Section 1, Introduction to PERT. What does it actually stand for? PERT stands for Program Evaluation and Review Technique. Basically, it's a project management tool explicitly designed to plan, schedule, and control complex projects. But the absolute most important part of that definition is right at the end, especially when task durations are uncertain. This is absolutely your ultimate tool for taming chaos when you're just not sure how things will play out. Now, what's really interesting is the contrast between PERT and another really popular tool you might know, CPM, or Critical Path Method. They're often used together, but they have completely fundamentally different worldviews. You see, CPM assumes deterministic times. That means fixed, guaranteed durations. You use CPM when you know exactly how long a task is going to take. PERT, on the other hand, totally embraces probability. It deals with uncertainty by using probabilistic time estimates when you just don't have that fixed guarantee. So when do we actually use this in the real world? Well, you deploy PERT when you're building something completely new. Think research and development or software development, areas where these specific tasks have literally never been done before. As humans, we suffer from the planning fallacy, right? We are notoriously terrible at estimating how long new tasks will take, so past data just isn't perfectly reliable. PERT is also incredibly useful when you absolutely need to quantify schedule risk, like figuring out the exact probability of finishing a project before a very strict client deadline.
Moving on to Section 2, the 3 time estimates. Because we don't have fixed times, PERT requires us to make 3 separate estimates for every single task. First up is the optimistic time, usually represented by the letter A. This is your absolute best-case scenario if everything goes perfectly. Second is the most likely time, or M, which is your best guess under normal, everyday conditions. And finally, the pessimistic time, or B. That is the maximum possible time if things go horribly wrong. By defining the best, worst, and most likely scenarios, we establish a really solid, realistic range of reality. All right, Section 3, core formulas and calculations. Let's get into the math behind the magic.
Here's our very first core formula, expected time, or TE. This calculates the weighted average of our 3 time estimates. And look at the narrative of the math happening here. We add the optimistic time, A, plus the pessimistic time, B, but we multiply the most likely time, M, by 4. Why do we do that? Because we want to give the most realistic scenario the heaviest weight in our calculation. Since we're adding 1A, 4 M's, and 1B, we have a total of 6 parts. So we divide the whole shebang by 6. It's actually a beautifully simple logic.
Our second core formula is for variance. This mathematically captures your level of doubt. We take the worst-case scenario, B, subtract the best-case scenario, A, divide that by 6, and square the whole result. What this is doing is looking at the spread between your pessimistic and optimistic times. Think about it. If your best case is 2 days and worst case is 3 days, your variance is tiny because you're pretty certain. But if your best case is 2 days and your worst case is 20 days, this formula is going to yield a massive variance, mathematically warning you of the high risk and uncertainty baked into that specific task.
Section 4, analyzing the critical path. Time to find the bottleneck. Let's look at a really straightforward 4-task project to see this in action. We have tasks A, B, C, and D. Tasks B and C depend on A, and task D depends on B and C both being finished. Notice how we plug our A, M, and B estimates right into those formulas we just learned. For task A, calculating 1 plus 4 times 2 plus 3, all divided by 6, gives us an expected time of exactly 2. We do this for every single task to get our baseline durations and variances. And hey, take a look at task C. Its best, worst, and most likely times are all exactly 1, so its variance is, mathematically, 0. There is absolutely 0 uncertainty there. Now we map the flow. To finish this project, we can either go through task B or task C. That gives us two distinct paths. Path 1 is A to B to D. Adding up those expected times we just found gives us 9.67 weeks. Path 2 is A to C to D, which only totals 7.0 weeks. So the crucial point is that because path A, B, D takes the longest at 9.67 weeks, it dictates our entire project's timeline. It's our critical path. It acts as the bottleneck, representing the absolute minimum possible timeline for the entire project.
Section 5. Measuring project schedule risk. Will we actually hit the deadline?
Now, just knowing the expected duration isn't quite enough. Let's say your client demands this project be done in exactly 11 weeks. Can you confidently promise that? Well, we use a Z-score formula to find out. T is our target deadline of 11 weeks. We subtract our expected project time of 9.67 weeks. Then we divide that by the project standard deviation. In our current example, adding the variances of the critical path, that's task A's 0.11, task B's 1, and task D's 0.11, gives us 1.22. The square root of that gives us a standard deviation of 1.1. Plugging that 1.1 into the bottom of our equation, we get a z-score of 1.21. When you look up a z-score of 1.21 on a standard probability table, it translates to 0.887, meaning you have an 88.7% probability of finishing this project within 11 weeks. I really want you to think about how powerful that is. This is the tangible, real-world value of PERT. You aren't just guessing anymore. You know mathematically that you have nearly a 90% chance of success before you have even spent a single dollar or started a single task.
All right, Section 6, the comprehensive master example. Prepare yourself because this is the final boss of the explainer. We are looking at a much more complex 9-task project, tasks A through I. You can see their complex web of predecessors, like for instance, task I cannot start until both G and H are totally finished. Right now, all we have are the raw inputs, just the baseline, optimistic, most likely, and pessimistic guesses for this massive undertaking. Now, let's move forward and see how this builds out when we apply our formulas. By running each task through our expected time and variance equations, our matrix really starts to fill out, and we can immediately see which tasks carry the most uncertainty. Take a look at the variance column for tasks B, D, and G. They all have a variance of 1, which is the highest on the board. As a project manager, those are your massive red flags. Those tasks have a really wide spread between best and worst case scenarios, and they absolutely need to be monitored closely. And here is the fully populated table, adding all of our scheduling calculations. We calculate the earliest start and finish times, along with the latest start and finish times for every single task. The difference between those gives us our float. Look closely at that far right column. Float basically represents how much a task can be delayed without delaying the entire project. Notice that tasks A, B, D, G, and I all have a float of 0. They have absolutely no wiggle room. That string of 0 float tasks mathematically dictates our critical path. To conclude our mathematical journey, we need to find the total project uncertainty. We do this by taking the sum of the unrounded variances strictly on our critical path. So the variances of A, B, D, G, and I, which equals roughly 3.888. Taking the square root of that gives us our project standard deviation of roughly 1.97 days. This number right here is our key. We can now use it with a z-score to predict exactly how likely we are to meet literally any stakeholder deadline requested for this massive 9-task project. And this brilliantly illustrates the entire system in one place. Honestly, I highly encourage you to take a quick screenshot right now. It is your master key. It contains the expected time formula to weight your most likely guesses, the variance formula to measure your doubt, the critical path definition, and the z-score equation to calculate your real-world probability of success. So, I want to leave you with this final thought. We've just seen how PERT can take raw, completely uncertain guesses and mathematically transform them into precise, calculated probabilities of success. If this tool can predict the unpredictable so reliably, what complex project in your own work are you currently mismanaging because you're just relying on fixed, deterministic guesswork? It's time to stop guessing and start calculating.